Today, we're taking a deep dive into a research about how we represent and understand 3D scenes with vision-only occupancy prediction. The two papers are GaussianFormer and its successor, GaussianFormer 2, authored by Tsinghua University, UC Berkeley, and Phigent Robotics. We will introduce the basic idea in the first version of GaussianFormer and then describe the improvements made upon it in GaussianFormer 2. To set the stage, let's consider the traditional approaches to 3D semantic occupancy prediction. Typically, we take camera images and try to infer which areas of the 3D environment are occupied and what semantic classes they belong to. The straightforward solution has been to discretize the 3D world into a massive grid of voxels and assign a semantic label to each voxel. While intuitive, this approach is computationally and memory intensive. Most of the scene is actually empty space, and by representing every cubic distance equally, we waste a tremendous amount of resources. Even planar representations like bird's eye view or tri-perspective view reduce complexity somewhat, but still struggle with modeling large empty regions. The inefficiency in handling mostly empty 3D space limits the size of the scene we can cover, prevents higher resolution, fine-grained detail capture, and computation speed. This is where GaussianFormer steps in. Instead of relying on dense fixed grids, GaussianFormer proposes representing the entire 3D scene as a set of 3D Gaussian primitives. So, what are these 3D Gaussians? Each Gaussian is a flexible, object-centric primitive defined by the following parameters. A mean m representing the center position in 3D, a scale vector s describing the size in 3D, a rotation quaternion r describing rotation in 3D, and semantic logits c that provide classification information. The covariance of the Gaussian is then derived from s and r. Here, each Gaussian acts like a soft continuous blob that can be stretched, rotated, and positioned to approximate different parts of the scene. By leveraging this representation, GaussianFormer drastically reduces the memory footprint. It needs only a sparse set of Gaussians to approximate what would otherwise require millions of voxels. How does GaussianFormer actually predict occupancy? It uses a transformer-based architecture with several key components. First, Gaussian queries and properties. The system maintains two sets of representations for each Gaussian. Gaussian queries are high-dimensional feature vectors that interact through transformer blocks, gathering contextual information from images and among themselves. Gaussian properties are physical parameters such as mean, scale, rotation, and semantics that define the actual Gaussian primitives. Second, the self-encoding module. This module applies 3D sparse convolutions on the Gaussians interpreted as points in 3D space, instead of expensive global operations. These sparse convolutions efficiently propagate information only where Gaussians are present, exploiting the inherent sparsity of driving scenes. Next, the image cross-attention module. Gaussians query multi-view camera images via a deformable attention mechanism. Each Gaussian generates 3D reference points, projects them onto the image planes using camera extrinsics and intrinsics, and retrieves relevant image features. This cross-attention step provides rich visual information that guides the refinement of Gaussian properties, including position, shape, and semantics. Lastly, we have the refinement module. After each round of self and cross-attention, an LP refines the Gaussian properties. Inspired by object detection frameworks like DTR, the refinement module uses the updated Gaussian queries to iteratively improve Gaussian properties. This iterative refinement ensures that each Gaussian converges to a stable configuration that accurately represents a portion of the scene. To recap, the system starts with a fixed number of these Gaussian queries, which can be considered as candidate embeddings, and iteratively refines them, attending to multi-view images and updating their latent representations. After each iteration of refinement, each candidate is decoded into a set of Gaussian properties. Of course, let's not forget that we still need one last step to convert the 3D Gaussians into 3D occupancy. This step is called Gaussian to voxel splatting. converting sparse Gaussians to dense occupancy. The 3D Gaussians are first embedded into the target voxel grid according to their means. This module approximates occupancy at a voxel by aggregating contributions only from Gaussians in its neighborhood, dramatically reducing computation. Formally, the occupancy value and semantic distribution at a point P is computed as a summation of exponential function of the distance from each neighboring Gaussians multiplied by semantic logits. While GaussianFormer significantly reduces memory usage by about 80% compared to voxel-based methods and achieves competitive performance, it still has two notable limitations. First, many Gaussians still end up describing empty regions, not fully solving the inefficiency of free space. Second, the direct summation of Gaussian contributions can lead to overlapping Gaussians. Without a constraint, Gaussians can pile up in the same region, resulting in unbounded semantic logits and unnecessary redundancy. This leads us to the second approach, GaussianFormer 2, building upon its predecessor. GaussianFormer 2 tackles these issues by adopting a probabilistic viewpoint and introduces several key innovations, namely probabilistic Gaussian superposition, semantics with Gaussian mixture model, and the distribution-based initialization. Let's go through them one by one. In GaussianFormer 2, the occupancy and semantics are handled separately. For occupancy, the key innovation for the probabilistic framework is to interpret each Gaussian instead of as an additive contributor, but as a probability distribution indicating how likely it is that its vicinity is occupied. Mathematically, a single Gaussian now is as follows. Alpha xg is the probability that the point x is occupied by that Gaussian g. To aggregate multiple Gaussians, GaussianFormer 2 uses the multiplication theorem of probability. This ensures that if any single Gaussian strongly indicates occupancy, alpha x will be high, taking away the incentive for multiple Gaussians to redundantly overlap in the same region. The occupancy probability saturates quickly and does not grow unboundedly with more Gaussians. Actually, the shift from summation to multiplication makes the probability to go lower the more Gaussians are overlapping, discourages unnecessary overlap, and keeps the representation object-centric. While geometry or occupancy part is handled by the probabilities alpha, the semantics are determined through a Gaussian mixture model. Here, P of x given Gi is the conditional probability of x under the this Gaussian distribution. AI represents an opacity or mixing weight, and Ci are softmax normalized semantic class distributions. This ensures that semantics are always properly normalized, eliminating unbounded logits and further reducing overlap-induced issues. In probabilistic formulation, Gaussians are supposed to model only occupied regions. Thus, it is important to initialize the Gaussians properly, instead of relying on random initialization or depth-based priors. GaussianFormer 2 learns pixel-aligned occupancy distributions directly from the training data. By casting rays into the scene and sampling points along them, the model acquires occupancy labels from ground truth data. It then trains a module to predict these occupancy distributions along each ray. This approach no longer depends on depth prior, which only captures the surfaces of objects. It ensures Gaussians start closer to actual objects, improving both speed and accuracy of convergence. Putting everything all together, GaussianFormer 2 surpasses the performance of original GaussianFormer and many other contemporary methods on challenging benchmarks like New Scenes and Kitty 360. It uses fewer Gaussians, therefore less memory, compared to the original GaussianFormer, and focuses them on actually occupied areas. In ablation studies, GaussianFormer 2 shows a higher percentage of Gaussians correctly positioned in occupied space, reduces the average distance of Gaussians to occupied voxels, and minimizes overlapping volumes. In summary, GaussianFormer introduced the idea of representing a scene as a collection of semantic Gaussians, dramatically reducing memory usage and still capturing fine-grained structural details. GaussianFormer 2 took it further by implementing a probabilistic perspective that restricts Gaussians to model only occupied regions, avoiding empty space redundancy, and employing a Gaussian mixture model for semantics to maintain bounded and meaningful class distributions. This line of work reflects a paradigm shift. We're moving away from uniform large-scale grids and towards sparse probabilistic and object-centric representations. That's it for today. Until next paper. Thank you.